So I want to thank the Radcliffe staff for making this sabbatical such a wonderful time. Also our dean, Elizabeth Cohen, and the staff, and also the fellows for providing a very interacting, stimulating environment. So I just realized that certainly more than half my sabbatical is over. Almost, I guess, really in 2 weeks, 2/3 of my sabbatical will be over. I should start contemplating how to get back. Need to. We have so much sport here, so it's going to be a challenge to adapt to the life in London. So today, my plan is to talk about two things most of the time in this talk. The first part will be like an introduction really to Bayesian statistical inference, what Markov Chain Monte Carlo means. And then the second part will be an introduction to Coalescent. So when we got those two things together, exciting things will happen, but then you can see what we are struggling with. So so I'm going to give you a very quick introduction to Bayesian statistics and Markov Chain Monte Carlo. So first, the concept of probability. Just want to mention what probability means in this context. It's a very basic terminology in statistics, but even today, after more than 100 years, it's very difficult to define. So here are two concepts. The first one is the frequentist definition. For example, I can say that if I have a fair coin, by that I mean the probability of hits is 1/2. Essentially, I'm saying that if I flip the coin many times, the proportion of the times I say hit becomes closer to 1/2. So that's a frequentist definition with probability defined as a proportion of frequency. A second definition is the Bayesian definition that's basically saying that a probability measures my degree of belief. Maybe when I say there's a chance or probability of 80% that it will snow tomorrow, I mean how much confidence I have in that statement. In particular, we don't have many repetitions of tomorrow. Sorry, that doesn't sound right. I think we do have many repetitions tomorrow. But you know what I mean. Yeah, tomorrow is after today. Yeah. Okay. So this pretty much divides statisticians into two big camps. The frequentist, or sometimes called the classical statistics, and the Bayesian. Oftentimes they don't talk to each other. So with this slide, you choose one definition, you stick to it. So in my talk today, I'm going to use the Bayesian definition, where the probability is a degree of our belief. You can be a bit more specific about this. And this then divides the Bayesians into two camps. The subjective Bayesians, they believe we can only talk about our personal subjective belief on any statement or anything that is uncertain. Or the objective Bayesians, who try to say that we can rationally measure our degree of belief. Unfortunately, I think the rational Bayesian or objective Bayesians have lost out. So now the Bayesian statisticians, they tend to be the subjective Bayesians. So I'll come to this in a slide later on, but as the term indicates, subjective Bayesians use subjective probabilities. My biologist colleagues all dislike this very much. They don't like our personal opinions to influence the statistical inference. But This is very much at the foundation of statistical inference. It's not very stable. Yeah. It's a lot of unstable ground. So similarly, we use statistical distributions to describe our uncertainties for any parameter or any number that we are interested in. So I want to explain. I'm starting from very low, so if you're a mathematician, this might be simple. But I'm not trivializing too much. So I'll just tell you that I have one slide with some equations, but not really many slides with equations. I just copy the equations back and forth. So, okay, so we use a statistical distribution to describe our uncertain knowledge about any parameter. Let's say that in this example, we have a parameter theta, that's the probability of hits for a coin. So obviously this goes from 0 to 1. So when we describe the uncertainty or uncertain knowledge about this parameter, we use statistical distributions. So I'm just using this simple example to explain how you rate a statistical distribution. So basically, you have this curve like this one. The area under the curve over an interval. For example, here it's from 0.1 to 0.2. The area here gives us the probability that this parameter theta is between 0.1 and 0.2. Obviously, the total area under the curve has to be 1. So that's all I did for my talk here. And then you can see that with this distribution, we think that theta is most likely around 0.5 because it's got a peak here. So if we talk about the 0.1 intervals of 0.1, so around 0.5, that interval will have a lot of area or probability mass, so it's more likely. Whereas extreme values close to 0 and 1 are less likely. With this distribution, we feel that theta is either close to 0 or close to 1. Okay, so that's how the distribution is interpreted. Now a question. I'm not going into this, but I just ask a question, you can think about it. Suppose I know nothing about this theta except that it's between 0 and 1. What kind of distribution describes my knowledge or my lack of knowledge? It's a good answer, yes. Some people think that this flat distribution might mean that you have no knowledge. But it's not generally accepted that's not true. So the short answer is that there's no such distribution that can represent total ignorance. That's also the reason why the objective Bayesians lost out. So the subjective Bayesians are having the day. Okay, so now this is my slide with a few simple equations. I'm going through this, and then the rest will follow rather easily. It's a simple case of estimating this probability. It's called a binomial probability, like the probability of hits. However, this was the problem that's dealt with in Thomas Bayes' famous paper, which obviously that's Bayesian statistics is named after him. This is long before statistics as a subject area existed. So also this has all the conceptual difficulties we face today. So we are interested in the parameter theta, that's probability of hits. The data we have are 4 hits out of 10 coin tosses. You can say immediately that 40% is a good estimate, right? Yeah, everybody can say that. So why are we spending so much energy on this? So the simple answer everybody can say will allow us to judge some principles. Yeah, you can formulate a principle. You can see how it works with this simple example. If you are happy, you can apply the principle to very big, complicated problems for which you don't have the intuition. So if we do Bayesian, we have to have a prior distribution for the parameter before we can look at the data, really, before we analyze the data. This is very much disturbing for some of my biologist colleagues. They say that I want to know this parameter. That's why I did experiment. I collect the data. Instead of you telling me what the parameter is, you are asking me to formulate a prior distribution to start with. What I. Fisher, the famous statistician, was trying to do that without this prior, but I think the effort is considered to be, in general, unsuccessful. One description is that he tried to make omelette without breaking the egg. Now, today we are with Bayesian, so whether you like it or not, we have to use a prior to start. Let's say that we use this uniform distribution as the prior. This is very commonly used. As Markov explained, some people have the impression that this is probably not adding any information on the parameter already. Thomas Bayes had a very long section trying to argue that this doesn't seem to be using any information or assuming any information. But in general, that's believed to be a failed attempt. So we have to have a prior for the parameter. Let's say we have the uniform. And the next component of the Bayesian inference is this likelihood, the concept likelihood. Likelihood means probability as well. They are just English words, they mean the same thing. But this term has been recruited in statistics to mean something in particular. So it's the probability of the data given the parameter theta. So in our case, we have 4 heads, 6 tails. So essentially, you multiply the probability of heads and the probabilities of tails. So you get, you write down theta 4 times. 1 minus theta, that's the probability of tails 6 times. You multiply them together. Some of you may notice this often. Sometimes there's a binomial coefficient there that's not important, so I don't have it here. So the idea of using the probability of the data to help us decide on the parameter values, that's due to R.A. Fisher. This is his paper of 1912 when he was a third-year undergraduate, so when he was 22. This is still fairly widely read. Yeah. I wonder how many of us write papers that are still read 100 years later. So the idea here is that we already have the data, 4 heads, 6 tails. We are interested in the probability of heads. Usually you use this formula to calculate the probability of the number of heads. When I tell you the probability of heads, you use the binomial formula. But this is an inverse problem of going from the data to the population to the parameter, or going from effect to the cause. So it's much more difficult. Anyway, Fisher's idea was that we could look at this probability of data for different values of theta. And then the particular value of theta that makes the data we observe look very likely will be favored. Does that make sense? Yeah, so we already have the data. And then given the probability of hit, like 0.4 or 0.5, we can calculate the probability of the data we already observed. And we choose the parameter value so that the data we already have a high probability. You can plot this as a function of theta. You'll find that the value of this probability for the data is larger when theta is 0.4 than when theta is 0.5. And then we think that the true theta is more likely to be 0.4 rather than 0.5. Yeah. It's not automatic. It's like a quantum leap in your mind. There are also controversies. Yeah, it's not really not all fixed. Okay, so we are go through the Bayesian procedure. We have the prior and the likelihood. So the likelihood really commonly accepted that they summarize the information in the data about the parameter theta. And then we have the posterior distribution, which gives us the distribution of theta when we have both the prior and the data. So in a way, the posterior combines information in the prior and the data. And the way that we combine the information is just to multiply those two pieces together. So that's this part here. So you multiply these two. Essentially, this gives us the relative preferences for different values of theta. However, one trouble comes in. When you multiply these two terms, this does not satisfy our requirement that the area under the curve is 1. So in the previous slide, I explained that with a statistical distribution, you want the area on the curve to be 1. But that's not satisfied when you just multiply those two together. In fact, you need to somehow rescale this so that this becomes a proper distribution with the area to be 1. So the numerator here, that's called the normalizing constant. It's normalizing the distribution so that the sum is 1. So in a way, if you multiply those two and plot here, you'll get a curve like this, but you don't really know the labels on the y-axis. So what this does is to allow us to put the numbers here on the y-axis so that the area under this curve is 1. That's my introduction to Bayesian statistical inference. I also explained that computationally it's difficult to calculate normalizing constant. So basically, this mathematics is an integral. When you have 3 parameters, you have a 3-dimensional integral that's really difficult to calculate. So now I'm going to move on to explain how you use Markov Chain Monte Carlo to avoid this calculation and still manage with the inference. Okay, so Markov Chain Monte Carlo. Monte Carlo. So first, Monte Carlo is the world-famous gambling city. Those things developed before Las Vegas became the top gambling city. So Monte Carlo, named after the gambling city, really means computer simulation using random numbers. So very briefly, I'll just have an example here to explain the basic idea. Suppose we want to estimate pi, which is 3.14 something. Nowadays we know. But suppose we want to use this kind of simulation or like gambling to estimate it. We can draw a square with side 2 At the inside, we draw a circle with a radius 1. And then we can flip a needle or ball onto the square. And then count the proportion of times that the ball hits the circle. So the square has an area of 4, and the circle has an area of pi. So the probability that we hit the circle is going to be pi over 4. Okay? So this way, just imagine that you threw a ball 1,000 times, you get 780 successes. I just made these things up. I didn't do the experiment. You can do it yourself at home if you like. So then the estimate of pi is going to be something like this. Yeah. So this idea is quite simple. So there was actually a famous experiment done by Buffon. Again, this is long before statistics existed, doing exactly this. So we are basically using random numbers as you do in a casino to do simulation. And then Markov chain, very briefly. Markov chain, a chain means a sequence. So essentially we get a sequence of values or states that have the so-called Markovian property. This is also called the memoryless property. Written in words, you say that given the present, the future does not depend on the past. I like this one very much because it describes my status very, very accurately. Memoryless property. So let's say that if we think like there are two kinds of weathers here, sunny and snow. And if we think that the chances for sunny or snow tomorrow only depend on today's weather, but not yesterday's or earlier, then you can just work out some probabilities for such transition from today's weather to tomorrow's weather. That means the sequence of the weather over the days will be a Markov chain. It has no memory. Given today's status, tomorrow's status will not depend on the past status. So I have talked about the two pieces in this name. Basically, Markov Chain Monte Carlo is a computer simulation algorithm that generates a sequence of values or states which form a Markov chain. So I'm now going to use that coin tossing example to explain how this works. So this is Markov Chain Monte Carlo. So sorry, my curve does not match the previous one I showed you, but this is supposed to show the product of the prior, the likelihood, which is not normalized. So we suppose we are somewhere with a certain theta value, and then we use a sliding window, a window around the current value, and to propose a new value. Let's say that we propose this theta star. So then we decide whether we will accept this new value. We do that by looking at whether we are going up or down. If we are going up, so this is the unnormalized posterior. If we are going up, we accept without any hesitation. Yeah. But if the proposed value is to go downhill, we don't reject it straight away, but we accept with a probability that's the ratio of the two heights. Let's say this is a 5. We are currently at 20. That's the height 20. So we calculate the ratio, which gives us a quarter. So we can flip a coin twice. If we get 2 hits, we accept. So we accept with probability 1/4. So that's the full algorithm. So every time you you propose a new value around your current value, and you decide whether you reject or accept. If you accept, you move to the new place, and then you repeat the algorithm. If you reject, you stay where you are, and you propose again. Okay, so then suppose this shows the running that algorithm twice, once with the blue dots, another with the red circles. So let's say that with the red one, I start from point 1. I propose a value that's like 0.155. And that's accepted, so I move to the new value. And then here, I'm at 0.322, I guess. I propose some values, but they are rejected. I stay here for quite some time before I move again. So those values that are visited form a Markov chain. You can say from that algorithm where we are moving to the next step only depends on where we are right now, but not in the not the states we visited in the past. So the magic of the algorithm is that those values that are visited are a sample from the posterior. So if you bin these values and draw a histogram, you find that you have this curve. This curve it matches the curve I showed you earlier very precisely. So I'm going to mention a few other features of the algorithm, which I more or less already touched on. The first is that sequence of states are visited form a Markov chain. So I explained this already. Given the current value, you don't need to know the past values to decide where you go. The second feature is that the state distribution of the chain is the posterior. What this means is that in the long run, we will be visiting the peak of the mountain more than the deep valleys. You can remember it's more or less a hill climbing algorithm. It tends to go uphill. But if it's going downhill, it tends to hesitate. So it will spend more time around the peak. Mathematically, you can prove that actually you're just visiting the distribution correctly. A third feature of this algorithm is that you don't need to know the posterior, the normalized posterior distribution. You can run this algorithm as long as you can calculate the ratio of the two posteriors. So the reason, I hesitate a little bit to write this, but it's just I copied the formula from the previous slide. So to decide whether we accept or reject, we need to calculate the ratio of the posterior for the new value of the parameter versus the posterior for the old value. So in the formula, we had this thing here that's in the numerator, it's the denominator. That occurs here, so we cancel this. Yeah. I think Manuas left the school a long time ago. So I went to the internet to search for some intuitive explanations of rules about cancellation, and I found something really exciting to show you. Here, this is so okay. Let's probably apply cancellation too aggressively. But you get the idea. So, yeah. Anyway, so the cancellation here is valid, and so we carry on with the algorithm. It may also be interesting to know that this Markov Chain Monte Carlo algorithm is the byproduct of the hydrogen bomb project. Maybe this is the best outcome of that project. The paper was published in 1953 by several famous physicists working in Los Alamos on the H-bomb. Okay, so this is my introduction to the Bayesian statistics. Now I go on to talk about genetics, the coalescent. So we have 22 chromosomes here. They are called autosomes, plus another pair of chromosomes that are called the 6 chromosomes, X and Y. So in the kind of work we do, we use genetics, these chromosomes or the DNA sequences, to trace the genealogical histories of individuals or human populations. So you can imagine that the Y chromosome traces the paternal history. So each boy has a father. The father has a father. So if you trace that paternal line, you can basically trace the history. So for 2 boys, you can trace the paternal lineages until you found a great-grandfather. The same thing for the male. For the female, you can use the mitochondrial genome to trace the maternal history. Now, for the autosomes, you have 2 chromosomes, one from the mom, another from the dad. And they have a complicated process of recombination. And as a result, the different segments of the genome can give us different histories. So this is like recombination. So in my talk here, so there are different ways of analyzing the data. In my talk here, I will just focus on short segments in the autosomes, so that the size or each segment has one history, but then the different segments have more or less independent histories. So we are going to use the short DNA sequences in the genome to look at their genealogical relationships and to trace the history. So here is one imaginary case. Let's say we have a population of only 10 individuals. It's a very small population. Each individual has 2 sequences. We can imagine those 2 are from one individual, and those are from another. So in the traditional population genetics, time runs forward. So those are the generations. So the sequences leave descendants, like parents have children. But we turn this process backwards in time. We focus on a sample. Let's say we have 5 sequences we sample today, and we trace their genealogical history backwards in time. So then we have this process that's called coalescent. So coalescent basically means the joining of the sequences when we found their common ancestor. So this model here is called the Fisher-Wright model, and this backwards view of the same process is called the coalescent. So let's go some pictures here. That's Fisher-Wright, and this is John Kimmel is responsible for developing the coalescent. Fisher is both a statistician and geneticist. Not ordinary ones, I suppose. So for 2 sequences, it takes on average 2 generations for them to find a common ancestor. So maybe intuitively you can think about a small village where they have inbreeding, they don't marry outside or with outside people. And then you can imagine that it's over just a few generations, two people will find a grandma or great-grandma. So coalescent happens much faster in a small population. So the average waiting time for the two sequences is 2n, which is the number of sequences, basically. So this explains that the population size determines the rate at which the coalescence happens. Just as a reference for the human population, we have the estimate of the average difference between any two human sequences. So that's slightly less than one difference per 1,000 sites or per kb. So this genetic variation measure is calculated using this result here. So the average waiting time is 2n generations. If the mutation rate is mu per generation, you just multiply the time with the rate to get the genetic distance. But you have two sides on this like pedigree or genealogical tree. So you multiply 2n by mu by 2, you get 4n mu, which gives us the average genetic distance between two sequences. So that's two genes or sequences. When you move to 20 sequences, here are some genealogical trees called gene trees, which we simulated. The first is that there's a lot of fluctuation in this process. So the waiting time can fluctuate a lot. The other feature is that the waiting time tends to be much longer when you have fewer lineages left. So on average, the last waiting time is half of the total waiting time for this sample. So that's coalescent. What I did with my collaborator, Bruce Ranala, is to extend this to the multi-species case. So the extension is very much trivial. So here we have two species or populations, A and B. So basically, when you have sequences from A, they can coalesce when you go backwards in time. But sequences from A, they cannot coalesce from sequences from B. So you have to wait until you reach the common ancestor. So apart from that, it's very much the single population coalescent. So I'm going to show you some results concerning human, chimp, gorilla, so these great apes. They use the George W. Bush as our representative of the human. But it doesn't matter who you use there. Yeah. But you can tell this slide is quite old. I just feel like some people feel nostalgic, I think. Okay, so for the so if you have a human sequence, a chimp sequence, a gorilla sequence from one segment, you may get a genealogical tree that's like the red one here. But if you look at another segment of the genome, you may have a tree that looks like the blue one here. So there are all three possibilities, which are listed here. So in this particular case, we have very stable estimates. So the human and chimp are close to each other in terms of the relationships. So 70% of genomic regions will share this relationship, but at 30% of the other genomic regions, the sequences have a different relationship as the species. To many people, this looks very surprising. But that's a very stable estimate. So this multi-species coalescent. it's very much similar to the single species version, except that we have species divergence times here, as well as the population size parameters, which set the rate of the coalescent. Okay, so we are using this multi-species coalescent to make many kinds of inferences. For example, we can do species delimitation, like trying to work out whether you have one species or two. We can estimate the phylogeny or the phylogenetic tree of the species. Quite a few of these Judith mentioned already. So I'm just going to show you a few slides. This one is somebody's analysis using those methods to decide that there were 4 giraffe species rather than 1. Species delimitation is one of the most controversial areas in biology. This also can generate a lot of controversies. So the data we have are a bit like this, just to give you a rough idea of what we are doing. So you have the sequence alignments from the genomes, and then we have some kind of model to describe the changes of those so-called nucleotides, TCAG, during the evolution. And then we essentially we have the species phylogeny. Given the species phylogeny, we have this genealogy describing the relationship of the sequences. And then we use models to calculate the probabilities. So again, we have to deal with the prior, the likelihood, which gave us the posterior. The algorithm is very much like that Hill-Calabi algorithm. I'm not going into the details, but you just change something in the program. You decide whether you are going to accept or reject. And then in the long run, you will be visiting the species tree in proportion to the posterior. So I'm going just to show you some of those algorithms for introducing changes can be very complex. So that's basically what we spend our time on. So I'm just going to show you one example about the gibbons. So here are those two are one species, and then there are 4 genera of gibbons. The phylogeny among those gibbons are very much unknown, very messy. And this indicates the messiness of the difficulty of working out the relationships. So we managed to use our program to analyze this large data set to get a tree. So I think I'm going to just quickly run to the end. So we got a tree that seems to be very reliable. And we did some simulations to ensure that the answers are trustable. The multi-species coalescent provides a powerful framework for analysis of the genomic sequence data. There are 2 approaches in using the framework to analyze real data. Some people go for the quick and dirty methods, but they are very powerful and can manage large data sets. We are going for the more delicate, sophisticated method, but we have a lot of trouble with the computation. Yeah. Our programs typically run for a few weeks, sometimes a few months. Okay, so I'm going to just acknowledge my collaborator, Bruce Ranala. He'll actually be visiting here next month in case you want to talk with him. So we are developing this method. Chen-Min did the analysis of the gibbon data. So I just show you one of these slides here. People are analyzing the lizards and frogs to work out their phylogenies. I like this because they are also playing a card game, apparently. They're just having some kind of tricks under the table. I think they are supposed to mean that the species actually hybridize. But here, I like it because the gambling, same way that we rely on those methods developed in the context of gambling to make genetic inference. I'm sorry, I'm a bit rushed at the end here. Thank you.